So in this lecture, this will probably be the final lecture on electricity, although I may have one more next week, we'll see. We're going to go further into talking about circuits. And so we'll start with a drawing of a series circuit, get some rules, and do some calculations. Then we'll look at a parallel circuits drawing. Once again, label the rules and do some calculations. I will then mention Kirchhoff's junction law and loop law, and then that should be it. For the homework assignment, we'll do a lab where you'll have to log on to a website and use a circuit building simulator. And then I'll also have some questions that go over parallel series circuit, and I think a little bit of Coulomb's law as well from last week. All right, so let's start with a drawing here of a series circuit. And we're going to go ahead and draw our battery. We said last week that the longer line is the positive symbol and the shorter line is the negative. And just because batteries pair together multiple cells, I'm going to have my symbol for a battery is going to look like this instead of just having it be short line, long line, but either way is okay. We're then going to have, when we say, this is a drawing for a series circuit. When I say something's in series, I'm referring not to the battery, right? Maybe this is a 9-volt battery. What I'm referring to are the resistors. And in this case, the resistors are going to be light bulbs again. If it was just a resistor without a bulb, the symbol would look like this. And that would be just a resistor. But our resistors are going to be light bulbs. So our symbol is kind of like this with the loop right there. And all right, so we'll have 3 of them, one after another. So when the bulbs are like this, we call them in series, kind of like Christmas lights, and that's about it. I know you might not think of it this way, but you can think of a bulb as having a positive end and a negative end, and so 2 ends to a light bulb there. All right, so we'll call this resistor 1, resistor 2, and resistor 3. And I'm going to go ahead and give them resistances to match those names. So a 1 ohm bulb, a 2 ohm bulb, and a 3 ohm bulb. Those are pretty tiny resistances, but it'll work for our example problem. All right, so some things to talk about when we have light bulbs in series. We always draw our battery the same way with the positive end on top and the negative end on bottom, because if we do that, we can think of current pointing in the same direction that positive charge would flow. Positive charge would move from this end of the battery, right, repelled by the positive end and attracted to the negative end. So I'm going to go ahead and draw current, because I'm pretty sure on some of these problems they're going to ask you to do that. So once again, the current's moving clockwise because we always draw our battery the same and our circuit the same. All right. So rules. Coming over to maybe this side of the paper and drawing this or writing these, we'll say our total, and these are series rules. So maybe I should, I'll just start writing them. All right, our total is equal to R1 plus R2 plus R3. And I'm going to write an ellipses there, because we can keep going, right? We don't have to stop at 3 resistors. There could be more resistors. And so there's our rule for calculating our total. Our rule for calculating the total current current is like water. Current is coulombs per second, is electrons per second. And what I mean by that is water. You can think of it like plumbing, meaning if 5 amps goes into this bulb, 5 amps comes out of this bulb. And if 5 amps goes into this bulb, 5 amps comes out of this bulb, and 5 amps goes into this bulb, 5 amps comes out of this bulb. And so there's still 5 amps right here and right here and right here. And it's just a pipe, right? And you might say, well, how is electricity accomplished? How do the light bulbs light up if current isn't used up? Well, voltage is what is used up, right? So we can say here that I total for the entire circuit is equal to I1. As I almost write, sorry about that, is equal to I2 is equal to I3. And once again, dot, right? And so what we're saying here is current is conserved. And I'm going to write like water. And this is due to two things, right? The first one obviously being the conservation of charge. Well, really, that's the only thing, right? The conservation of charge. Electrons are conserved. Charge is conserved. Electrons aren't destroyed. Matter isn't destroyed because electrons are matter. But we can also notice that this is reflected in Kirchhoff's, I think there's 2 H's in Kirchhoff. Kirchhoff's loop law, or I'm sorry, junction law. It's also reflected in Kirchhoff's junction law. And I'll talk about what that means here in a little bit. Okay, so we got one rule for resistance, a rule for current due to conservation of charge and Kirchhoff's junction law. Let's get a rule for voltage. Our total voltage in a series circuit is going to equal V1 plus V2 plus V3 ... And so what we're saying here is that this obeys Kirchhoff, 2 H's, Kirchhoff's loop law. And what the loop law says, and I guess I can talk about both of these kind of quickly, is that Kirchhoff's, if I go back to the junction law just says that at a junction, if, say, I'll make up a number, 10 amps goes into a junction. A junction is just somewhere where the pipe splits, right? The wires split. If 10 amps goes into this junction and 2 amps comes out here, right? Then how much comes out right here? Well, 10 amps goes in, 2 amps comes out here, and current's conserved, you would say 8 amps, right? And that's Kirchhoff's junction law. Pretty simple, right? Loop law is also kind of simple, but at the same time, these two laws are used to explain some complicated circuits. Says that this voltage of the battery you can think of as like positive 9 volts. And the voltage across V1 across this bulb, V2 across this bulb, and V3 across this bulb, you can think of as negative voltages. So you're going to spend all 9 volts going across these, and by the time you get to the end, you'll have 0 volts. So you have to drop all of your voltage through your circuit. So we also call the amount of voltage you spend at, say, bulb 1, we call it a voltage drop. What's the voltage drop across bulb 1? What's the voltage drop across bulb 2? What's the voltage drop across bulb 3? That would be V1, V2, V3. That's what I'm referring to down here. So the 9 volts that you started with is going to be canceled by negative voltages here. Now, usually I just call these positive voltages, and I don't worry about the fact that they're negative, but they are negative, and Kirchhoff's loop law addresses that, because Kirchhoff's loop law says that the sum of all of the change in voltages must equal 0. So when you have a positive 9 here, you have to have, say, a -1, a -2, and maybe a -6, right? Because -1 plus -2 plus -6 is -9. So this would be positive 9, and these three would account for the -9. The sum of the change in voltages, right? Positive 9 and -9 must equal 0. All right, that's Kirchhoff's loop law, and I'll kind of maybe reference those, or like I said, at the end I'll have we'll make sure we define those again just so we know. All right, so that's kind of it for series circuits. Let's do some calculations here, right? And do I have room at the bottom? Possibly. Kind of getting a lot on this piece of paper. Let's try it, right? Why not? Okay. So let's start with calculating some of the totals, calculating some of the individual values. These are questions I would ask you, say, on a quiz, right? So the first question I might ask is, what is the total voltage of this circuit? And you would say, well, you just read the battery. It's 9 volts. All right. Next question I might ask, what is the R total of this circuit? And you would say, well, R total is equal to, maybe I should put so what we're trying to solve here, R total is equal to R1 plus R2 plus R3, right? So it's going to equal 1 ohm plus 2 ohms plus 3 ohms, which is equal to 6 ohms. All right, so far so good, fairly simple. Then the next question might be I total. And now you're thinking, well, it's not as easy to see an I total up here. How are we going to get that? Well, remember Ohm's law, right? What was Ohm's law? Well, we learned it last time, right? Ohm's law, if I make a little space here, states V equals IR. And so Ohm's law is still something that we're going to rely upon here. And we'll just rearrange it and say I total then is equal to V total over R total. So we can write Ohm's law as long as all of these are totals. And that's what we're going to do. So we'll calculate I total here. I total then is equal to 9 volts divided by 6 ohms, which is 1.5 units. There are amps or amperes. Whoops, should have used my blue marker. All right, very good. So then the next question is, well, what is the current across the I across each bulb? What's I1? What's I2? What's I3? And you might say, well, I remember, because we just learned this, that I total, or I1, equals I2 equals I3 equals I total is equal to 1.5 amps. So if I asked on a problem or on a quiz, what is the current across bulb 1? You would say 1.5 amps. What is the current across bulb 2? 1.5 amps. And bulb 3, 1.5 amps. All right, so we got that right there. Now, the final question, the only one we haven't asked yet, right, is the individual voltages and resistances. Well, the resistances R1, R2, and R3 we were given with the problem, but V1, V2, V3 we don't know. So once again, we can come back to Ohm's law, but now we can write this individually for bulb 1, for bulb 2, and bulb 3 to calculate V1, V2, and V3. Now we know they have to add up to 9, but we don't know any of the numbers, so we can't really use that right now, right? So let's go ahead and use Ohm's law individually for each bulb. V1 equals I1 times R1, right? And starting with bulb 1. So we can say that V1 is equal to I1, which is 1.5 amps, times R1, which this is a 1 ohm bulb. What's 1 times 1.5? We just say 1.5 volts. Now, could I have just used the symbol V? Yeah, but I just wanted to make sure, well, kind of running out of room, wanted to make sure that that it's clear. So I just wrote out the word volts. Okay, let's do the same thing for bulb 2. V2 is equal to I2 times R2. So see how we use Ohm's law for an individual bulb, and we were using it for the total. As long as you stay consistent, you're okay. All right, V2 is equal to I2, which is 1.5 amps, obviously, times R2, which is a 2 ohm bulb. 2 times 1.5 is 3 volts. Okay, so far so good. And finally, V3 is equal to I3 times R3. All right, V3 is equal to, well, I3 is 1.5 amps. R3 is 3 ohms. So 3 times 1.5, that's going to be like 3 times 15, so 45, and so move the decimal, 4.5. All right. Now a good check here would be to say, well, is V total equal to V1 plus V2 plus V3? Well, V total is 9 volts. Is 1.5 plus 4.5? That's 6, right? Plus 3, that's 9. Is 9 equal to 9? Yes, it is. And so we did it correctly, and we are right. Also, you can think about Kirchhoff's loop law, right? Is this being a positive 9 volts and these being negative values across V1, V2, V3 all being negative. So is 9 volts plus negative 1.5 plus negative 3 plus negative 4.5 equal to 0? Yes. The sum and the change of the voltages is 0. Kirchhoff's junction law, is it obeyed? Yeah, there's no junctions here. So, right, it's just a straight line of wire or pipe or whatever for the water to flow through. And so therefore, it stays a constant 1.5 amps, so it obeys Kirchhoff's junction law as well. All right, so that is all we have there for series circuits, and hopefully you can see all that, and we're good. All right, let's talk about parallel circuits. All right, so just like last time, let's start with the drawing. Of a parallel circuit. Okay, drawing of a parallel circuit. Let's go ahead and give it a 9-volt battery, just like last time. Once again, I'm going to use the same symbol for my battery. I'm just going to label the ends and not anything in the middle, but this would be a positive and this would be a negative. All right. So with a parallel circuit, what we have that makes us different is we have multiple paths for the current. The current can go this way, the current can go this way, and the current can go this way. And each path that it travels through has a bulb. All right, let's go ahead and call these, we'll say this is R1. And once again, we'll make it equal to 1 ohm. We'll call this one R2. And we'll say it's equal to 2 ohms. Running out of room. And finally, this one will be R3, and this will equal 3 ohms. All right. We'll go ahead and draw the current. Once again, current is going to go from positive to negative. But we can see here that while this is going to be the total current right here, right? This, when it gets to this junction, it's going to start to become different. I'm sorry. It's going to start to become different. And in fact, when the current passes over this bulb or through this bulb here, that will be I1. And then some amount of current's going to leave here. We don't really know what that is, but we do know when it passes right through here, this will be I2. And when it passes through right here, this will be I3. Okay, interesting. All right, and then when it comes all back together right here, it'll be back to being I total because current is conserved. All right, so I think we're starting to get at some of the rules here already. Let's start with, I guess we can start with that rule right there, that I total has to be equal to I1 plus I2 plus I3. And this is based on conservation of charge and Kirchhoff's junction law. So let's go ahead and write that down. I total equals I1 plus I2 plus I3 ... And there's no reason they all have to be equal, right? And they're not going to be unless these were the same resistance. So we're going to see here that it follows the junction law, which states that when it gets to this junction, that if maybe 10 goes in and 2 comes out this way, right, then 8 would go out this way. And what is what is that current? Why does that matter? Well, if 8 comes out this way and we get to this junction and 4, and we'll say 3 goes down here, then and we have I think we said 8, right? 8 comes in and 3 goes down, then 5 goes this way. All right, so you can see that the junction law has to be followed throughout the circuit. All right, let's go to the next one. This one's kind of interesting. So this is going to be a 9-volt battery. And Kirchhoff's loop law said that each loop, complete loop of the circuit, you have to have the change in voltage equals 0. So if you add 9 here and you go through a loop of the circuit, you have to spend 9 right here. So what we're saying here is that V1 across this bulb has to equal 9 volts. And for this loop of the circuit, that is also a complete loop, right? So you have to once again drop 9 volts. So V2 is equal to 9 volts. Now this doesn't make this a magic battery, right? Because V3 is also 9 volts. And what I mean by that is this is not a 27-volt battery. So I am saying here then that V total, I'm going to draw a line right there. V total is equal to V1, is equal to V2, is equal to V3 because of Kirchhoff's loop law. 2 H's. That for each loop, you have to be able to, if you add 9 from the battery, you have to drop 9 in that loop. So the change has to be 0, right? We call this a positive 9 and this a negative 9. So it kind of looks like this, right? For Kirchhoff's loop law, sigma delta V is equal to 0, and we would just say positive 9 from the battery plus negative 9 from the bulb. And is that equal to 0? And the answer is yes. So Kirchhoff's loop law is working, is what that is what happens. So this is why each bulb gets full access to the battery. All right, the last one, resistance. And this is pretty much when you think of a parallel circuit, this is the formula that you're given, and it's kind of a crazy formula because this is one of the only formulas where the thing you might want, which is the total resistance, doesn't start on top. It starts on the bottom of a fraction. So we say 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay. So kind of a different formula, one you might not have seen before. Now, why is this important, or how does this make sense? What this formula says, and this is kind of a key idea, is that for series circuits, let me write this down. So going back to, before I explain this, let me point out why this is different from series. In series circuits, resistance increases with more bulbs. All right, that made sense, right? Based on last time's formula. But parallel circuits an increase in resistors lowers the increase in, I want to say resistors, or I want to say paths. I'll say both. Increasing resistors / paths lowers. So this was total resistance. So this lowers the total resistance. So by having more paths with a resistor, the resistance lowers. So right away, that should seem maybe kind of obvious, because when you tack on another resistor, like if I put a 4 ohm resistor right here, I can guarantee you the resistance would be lower than what it is right now by adding another path. So when you have another path, you have another place for a current to go. And because of that, increasing resistors and paths lowers the total resistance. All right, I don't expect that to make sense right away. So maybe let me make an analogy here. Let's say you were at Meijer and there was one cashier doing an awesome job, right? A super low resistance. So resistance of 1 ohms. And in electrons, the people, you're like an electron, and you go through this path, past this cashier, pay for all your stuff, and leave. And that's great, right? But what if we opened another lane and this cashier wasn't as good, right? They had a resistance of 2 ohms. Now you might say, well, that's a slower path, right? Yeah, obviously, right? When I go to Meijer, I always try and find out who the fastest cashiers are and go through that line. So in this case, even though that might be slower, do more total people get through the line quicker with 2 lines open? And the answer is obviously yes. So this lowers the total resistance. So let's go back for a second. What's the total resistance right now with just 1 line open? You would say, well, this is a 1 ohm bulb. Total resistance is 1 ohm. Okay, What is it now with two lines open? Well, you just said it had to be lower than, and it's got to be a lower total resistance with two lines open. So I can guarantee you, I haven't done the calculation, but it's smaller than 1. All right, well, that the total resistance would be smaller than 1. And that's what this formula allows us to calculate. All right, so what if we open a third line? Well, then it would be even smaller still, even though this is the worst cashier ever, right? Maybe they're new and they don't know what they're doing, and they have a 3 ohm resistance. Well, this has to be not only smaller than 1, but smaller than the previous answer, whatever that was. Maybe it was 0.75. So maybe this is going to be like 0.4 now, the total resistance of the circuit. All right, so okay, so hopefully that makes a little more sense now why the resistance is lower. So I can write that one more way. I can say that R total, or I can think of it one more way. I can say for parallel circuits, or resistors in parallel circuits, right? For parallel circuits and their resistors, R total must be smaller than the smallest resistor. So we can say right now, and be correct for our circuit, that R total must be less than R1, right? So, which is 1 ohm. Now we haven't calculated R total, but we know that this is the case, right? This is 1 ohm. Okay. All right, I think that's about all I wanted to say there. Let's go to calculations, right? Just like we did last time. I'm running out of room, and so I'm just going to get another page because otherwise it's going to get kind of crazy, and we'll go to another page. All right, so first question, V total. Remember, it's not a magic battery. It's just obeying Kirchhoff's loop law. So even though it looks like 9 volts plus 9 volts plus 9 volts, no, that doesn't work that way. It is just a 9-volt battery, even though each ball pulls on the 9-volt battery and draws on it. A question that showed up on the AP test one year was, well, you have this happening and you have your series one happening, right? Like it was, and it was which battery drains the fastest. And because this pulls on the battery and it with 3 different bulbs at 9 volts, this battery does drain faster than this one. Okay, so like I said, it's not a magic battery. You are pulling on the battery harder here by having full access to the battery in each location. So that was kind of a cool question. All right, so let's come back to this. So V total is equal to 9 volts. All right, next question. What is the voltage across bulb 1, bulb 2, and bulb 3? Well, whoops, there's my blue marker. Okay. Well, you would say V1 equals V2 is equal to V3 is equal to V total is equal to 9 volts. So if they asked you what was the voltage drop across, and remember, these are voltage drops too. Because I always have kids ask me that. We'll be doing a worksheet, and they'll be like, what's a voltage drop? And right? Because these are actually negative 9 volts, right? That's why we call them a drop. And this is a positive 9 volts from the battery. So this would be 9 volts, 9 volts, 9 volts in magnitude, right? And that's equal to the 9 volts from the battery, right? Okay, so those are the voltage drops across bulb 1, bulb 2. Voltage drop across bulb 3 is all 9 volts, negative 9 volts. All right, good. Let's go to what's next. I1, I2, and I3. Maybe we want to know let's learn those first, and then I think we can go to the total. Now, why am I going in this order? You might say, well, I'm kind of jumping around. You did total first, you did individual next. Why is that? Well, I'm going in the order that makes that we can do. So a lot of times with circuit problems, you kind of have to go in the order that makes the most sense for that problem. So you can't just be like, oh, well, I'm going to do total voltage, total current next. You can't have a set order all the time because it's going to depend on the problem. So there is another order I could have went here. I could have got that R formula out right away and tried that new R formula, but I didn't, right? So I'm doing it this way instead. All right, I2 equals, so I'm using Ohm's law and writing it for each bulb. And I'm going to get each individual current because I know V1, V2, V3, and they told us R1, R2, R3, right? 1, 2, 3 ohms. So we can make these calculations and get the individual currents. All right, so once again, bulb 1 gets the full 9 volts. And we can say I1 is equal to 9 amps. All right. I2 is equal to 9 volts over 2 ohms. I2 is equal to 4.5 amps. So once again, we're seeing, although current is still conserved, there's no reason that I1 has to be the same as I2, right? There's multiple paths and there's different resistances. So we're seeing that different amounts of charge can get through, different amounts of electrons can get through based on the resistance. When there's less resistance, more current gets through. When there's more resistance, less current gets through. That makes perfect sense. All right. And when there's even more resistance, even less current gets through, right? Whoops, blue marker. Okay, now total current, right? We said that current is conserved. If 9 amps goes through one branch, 4.5 through the next, 3 through the next, well, wouldn't you know then that I total has to equal I1 plus I2 plus I3, which is the same as me saying 9 plus 4.5 plus 3. That's equal to 7.5 and 9, so 16.5 amps. That's a large amount of current. But once again, I told you guys that these resistances are super low. They should be much higher, but whatever. It works. It's nice numbers to work with. All right, 16.5 amps. And that is going to be our total current, right? Okay, so pretty good. What can we do with that? Well, we know V total and we know I total. And so instead of getting R total using our cool new formula, let's get it just using Ohm's law, right? If we can, let me see if I can draw that right there. All right, so let's do it that way, right? Let's say I total is equal to, or I'm sorry, R total, jeez. R total is equal to what? Well, V equals IR, so R equals V over I. All right, so R total is equal to total voltage, which is 9, total divided by total current, which is 16.5. And remember we stipulated something? We said that R total in parallel needs to be smaller than 1 ohm. Remember saying that, right? Okay, so is this going to be smaller than 1? 9 divided by 16.5? Yeah, heck yeah it is. Let's go ahead and crunch it real quick. So 9 divided by 16.5 is 0.545. So I'm going to go with 0.55. Whoops, geez. R total is equal to 0.55, and units here are going to be ohms. So everything is checking out, right? It's smaller than the smallest resistor, which we said is true. All right. So you might say, well, that's a little bit of a letdown with that new formula. We never even got to use it. Let's go ahead and use it, right? Let's check and see if it works with the new formula, if it's really 0.55 ohms. So the new formula was 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. All right, 1 over R total then is equal to 1 over 1 plus 1 over 2 plus 1 over 3. Ugh, gross. Bunch of fractions not with common denominator, common denominators. So let's get some common denominators. So what's the lowest common factor? It's the number that I can multiply. I'm going to multiply these all by 1 to get a common denominator on bottom. So I think it's going to be, common denominator is going to be 6, right? So I'm going to multiply this one by 2 over 2, which is 1. I'm going to multiply this one by 3 over 3, which is 1. And I'm going to multiply this one by 6 over 6, which is 1, right? Okay, so it's going to look like this then. This is going to become 6 over 6 ohms. Ugh. This is going to become 3 over 6 ohms, still a half, right? We didn't change anything. And this is going to be still a third. This is going to become 2 over 6 ohms. But by doing that, now I have common denominators everywhere. Okay, so you might say, well, can I just flip everything? And this, I always get students that want to do this. Just flip everything, right? Why not? It's got to work. No, it doesn't. And here's why, because of the plus signs. When you don't have these, you have this equation, you can just flip both sides. But these plus signs screw that up. All right, so don't do that. All right, so let's go ahead and add now. So 1 over R total then is equal to, we can add the top, 6 plus 3 plus 2 is 11. And the bottom stays the common denominator, which is 6 ohms. Now we can do two things. We can, there's a couple ways to solve this. We can just get this as a decimal, and then write it over 1 and then cross multiply. I don't know. There's a complicated way to do it. I'm not going to show you that. I'm going to instead just cross multiply, right? It's in perfect form right now just to cross multiply. But I did say, well, we just flip both sides, and that's really what cross multiplying is going to do, right? It's going to be the same. So let's, maybe I can do that two ways. Let me cross multiply here. So we get 11 times R total is equal to 1 times 6. Divide both sides by 11, right? So we get R total equals 6 ohms over 11. All right, 6 divided by 11. Get my calculator. Ugh, where'd that tangent come from? It's probably when I dropped it. Okay, 6 divided by 11, 0.55. Aha. So it works, right? All right, what if we just flipped both sides, right? What if we just did the flip method? Well, let's flip this side. R total on top. Flip this side. 6 on top. Same thing, right? So once again, you can't flip though with those addition signs there. You can only do that when it gets to the cross multiplying stage. All right, cool. So it works. So the new formula works. It's kind of a pain to use. So you might say, well, why do I need it if I have Ohm's law? Why do I have to use the new formula? Right? Because it looked like, a second ago, Ohm's law works just fine. Why do I got to use this stupid formula? Because sometimes you're going to be given a calculation where you won't know I total, right? And if you don't know I total, you can't use Ohm's law, and you're stuck with the unfriendly formula that you have here. Okay, so I also promised that last time I would talk about Kirchhoff's laws, so I'm just going to do one quick thing before we call it good on the lectures and just show you this. And if you want to jot this down, you can. If you don't want to, that's fine. So once again, junction law sum of the currents in equals sum of the currents out. Looks a little unfriendly, but it's pretty much common sense. 10 amps goes into a junction, 3 amps goes out this way. How much comes out here? It would have to be 7 because current is conserved. So this is a consequence of the conservation of charge or current. Current is just charge per second, right? And remember, charge is really electrons. Okay, but we think of charge as the direction of positive charge moving through a circuit because that's what they thought of it when they discovered it, even though electrons actually move the other way. It's kind of weird, but that's what's going on. Let's look at Kirchhoff's loop law. Loop law just says the sum of the voltage changes must be 0. Batteries have positive voltages, resistances have negative voltages. We call those voltage drops. For a loop of the circuit, this change is 0. Sometimes a loop is the entire circuit, and sometimes it ain't, right? And we saw where today a loop of the circuit wasn't the entire circuit, right? This was a loop and got -9. This was a loop and had -9. This was a loop and had -9. And this has 9. Notice a lot of times we ignore that negative sign. We just deal with magnitudes, though, when we are working through calculations, right? So you can do that, and that's fine to ignore that. But realize that it's actually there, right? When you do the calculations, you don't worry about it. All right, so there's our lectures. We're going to have a lab to complete and then a quiz review, and that should be good for this week. All right, I hope you're having a good week and staying safe. And even though the weather's getting warmer, still be safe and make sure you still get outside and because it is nice. But yeah, all right, take care. And I'll have another lecture for you next week. And I think next week we're going to move on to sound. So, all right, see you then.